Hello, welcome to the video lecture series on digital image processing. For our last few classes, we have talked about different types of image restoration techniques. In today's lecture, we are going to talk about another topic which is called image registration. So, in our last few lectures, we have talked about restoration of degraded image. We have seen different techniques for estimation of the degradation model, and the different model estimation techniques we have discussed are the estimation of the degradation model by observation, estimation of the degradation model by experimentation, and the mathematical modeling of degradation. And once you have the model, the degradation model, then we have talked about the restoration techniques for restoring a degraded image. So, among the different restoration techniques, we have talked about the inverse filtering technique, we have talked about minimum mean square error or Wiener filtering technique, we have talked about the constrained least square filtering approach, and we have also talked about the restoration of an image if the image is contaminated by periodic noise. So, in such case, we have seen that if we take the Fourier transform of the degraded image, if the image is actually degraded by periodic noise or a combination of periodic noise, then those noise components, the noise frequencies appear as very bright spots, very bright dots in the Fourier transformation or in the frequency plane. So, there we can apply a band reject filter or sometimes notch filter to remove that particular frequency component of the Fourier transform, and after performing the band reject operation, whatever is remaining, if we take the inverse Fourier transformation of that, then we get the restored image which is free from the periodic noise. So, in today's lecture, we will talk about the image registration techniques. So, we will see what is image registration. Then when we go for image registration, then we have to think of the mismatch or match measures. So, we will talk about the different mismatch or match measures or similarity measures. We will see that whether the cross correlation, or we will see what is the cross correlation between two images, and we will also see whether this cross correlation can be used as a similarity measure when we go for image registration. And then we will talk about some applications of this image registration techniques with examples. So, by image registration, what we mean is that the registration is a process which makes the pixels in two images precisely coincide to the same points in the scene. So, by registration, what we mean is, if we are having two images of the same scene, maybe the images, two or more images are acquired with different sensors located at different positions, or maybe the images are acquired using the same sensor, but at different time instants, at different instants of time. So, in such cases, if we can find out for every pixel in one image the corresponding pixel in the other image or other images, that is the process of registration or the process of matching, and this has various applications that we will talk about a bit later. So, once registered, the images can be combined or fused. This is called fusion or combination. So, once we have the images from different sensors, may be located at different locations, or maybe if it is a remote sensing image taken through a satellite, where we have images taken in different bands of frequencies, then if we register all those different images, then those images can be combined or they can be fused, so that the information extraction or the image, the fused image becomes more rich in the information content. So, once registered, the images can be combined or fused in a way that improves the information extraction process, because this fused image, now they have combination of the information from different images or from different bands of frequencies, they will have more information, or they will be more rich in the information content. So, this image registration techniques has many applications. The first application we have already said, that the stereo imaging technique. In stereo imaging, what we do is, we take the image of the same scene or the images of the same object by two cameras which are slightly displaced, and there we have assumed that the cameras are otherwise identical, that is only apart from the displacement along a particular axis, the y axis or x axis, the features of the cameras are identical, that is they have the same focal length, same view angle and all these things. So, once I acquire these two images, that one of them we call as left image, the other one is called as right image, then if I go for this point by point correspondence, that is for a particular point in the left image, if I can find out what is the corresponding point in the right image, then from these two I can find out what is the disparity for that particular point location. And if this disparity is obtained for all the points in the image, then from the disparity we can find out what is the depth or the distance of the different object points from the camera. So, that is in case of stereo imaging, we have to find out this point correspondence or the point registration, or this is also called point matching. The other application that we have just said, that in remote sensing, where the images may be taken by different sensors working in different bands, even the sensors may be located in different locations. So, the images of the same scene are taken by different sensors working in different bands, they are also in different geometrical locations. There also, if we go for image registration, that is point by point correspondence among different images, then we can fuse those different images, or you can combine those different images, so that your fused image become more rich in terms of information content. So, the information extraction from such fused images becomes much more easy. The other application, again, the images may be taken at different times. So, if the images are taken at different times, and in all those images, if we can register those images, that is we can find out which is the point at a particular point for a particular point in a given image, what is the corresponding point in the other image which is taken at some other time instant. Then by this registration we can find out what is the variation at different point locations in the scene, and from these variations we can extract many informations like say vegetation growth, or maybe the land erosion, deforestation, or the occurrence of a fire. So, all these different informations can be obtained when we go for registration of the images which are taken at different instants of time. There are other applications like finding a place in a picture where it matches a given pattern. So, here we have a small image which is known as a pattern or a template, and we want to find out that in another image which is usually of bigger size, where does this template match the best. Now, this has various applications like automated navigation, where we want to find out that what is the location of a particular object with respect to a map. So, in such automated navigation applications, this pattern matching or template matching is very, very important. So, this image registration techniques or the image registration methods has various other applications and which can be exploited once the registration techniques are known. Now, to explain the registration techniques, let us take the first example, that example of the template matching. So, for this template matching, we take a template of a smaller size, we call the template to be a template F. Say F is a two-dimensional image of a smaller size, and we have an image G which is of bigger size. So, the problem of template matching is to find out where this F, the template F, matches best in the given image G. So, this F is called a template, or it is also called a pattern. So, our aim is that given a very big image, say G, a 2-dimensional image G, and a template F, which is usually of size smaller than that of G, we want to find out that where this template F matches best in the image G. So, to find out where the template F matches best in the given image G, we have to have some measure of matching, which is called which may be termed as mismatch measure, or the opposite of this, that is the match measure or the similarity measure. So, we have to take different match or similarity measures. So, we call them match measure or similarity measure, to find out where this template F matches the best in the given image G. So, there are various such match or mismatch measures, and let us see that what are the different measures that can be used. So, we have the given image G, G is the given image, and we have the template F. So, F is the template. So, we have to find out the measure of similarity between a region of the image G and the template F. So, there are various ways in which this similarity can be measured, so that we can find out the match between F and G over a certain region, say given by A. So, one of the similarity measure, the simplest similarity measure is we take the difference of F and G So, we take the absolute difference between F and G and find out the maximum of the absolute difference, and this maximum has to be computed over the region, say A. The other similarity measure can be that again we take the absolute difference of F and G and then integrate this absolute difference over the same region A. The other similarity measure can be you take F minus G, the difference between F and G, and the square of this, and take the integration of this over the same region, say A. So, you find that in the first case, when it is the difference between F and G. So, when I am talking about the difference, it is pixel by pixel difference. So, we take the difference between F and G, take the absolute value and the maximum of that computed over the given region A. In the second case, it is F minus G, again the absolute value, and this is integrated over the given region A. So, this is in the analog case. If I convert this in the digital form, this will take the form as F I j minus G I j, where I j is the pixel location, absolute value of this, and you take the double summation for all I and j in the given region A. So, you find that this is nothing but what is called the sum of the absolute difference. So, sum of absolute difference between the image G and the template F over the region A. And if I convert this expression again in the digital form, this becomes F I j minus G I j square of this and take the double summation for all I j belonging to that region A. So, this is nothing but sum of the difference squares. So, if I say that f I j minus g I j is the difference between two images or the error. So, this last expression, that is f minus g square integration over A, double integration over A, in the digital domain it becomes f I j minus g I j square, take the double summation for all I j in the region A. This is something equivalent to sum of square error. Now, out of these three different measures, it is the last one, g f minus g square integration. This is very interesting. So, if I expand this term, say f minus g square double integration over the region A, if I expand this, then this becomes double integration f square plus double integration g square minus 2 into double integration f into g. So, all these double integration are to be taken over the given region A. Now, you find that for a given image, this double integration f square, this is fixed, for a given template this is fixed, and also for a given image over the region A, this double integration g square, this is also fixed. Now, what is this f minus g square, sum of this? This is nothing but a sum of the square differences. That means, this gives the degree of mismatch, or this is nothing but the mismatch measure. Okay. So, if this f minus g square integration over the region A is minimum, because this is the mismatch measure. So, wherever this is minimum, at that particular location f matches the best over that region, that particular region of G. Now, when I expand this, this becomes integration double integration f square plus double integration g square minus twice into double integration f into g, and as I said that for a given template f square is fixed, and for a given image and a given region g square is also fixed. That means, this f minus g square integration, this will be minimum when this f into g double integration, this term will be maximum. So, whenever the mismatch measure is minimum, that will lead to f into g double integration over the region A, this will be maximum. So, when f minus g square double integration is taken as the measure of mismatch, we can take the double integration f into g over the region given region A, this to be the match measure or the similarity measure. So, this means that whenever the given template matches the best in a particular region, in a particular portion of the given image G, in that case f into g double integration over the region A will have a maximum value, and we take this as the similarity measure or the match measure. Now, the same conclusion can also be drawn from what is called Cauchy-Schwarz inequality. So, this Cauchy-Schwarz inequality says that double integration of f into g, this is less than or equal to square root of double integration of f square into double integration of g square. And these two terms will be equal only when g is equal to some constant c times f. So, this Cauchy-Schwarz inequality says that f into g double integration will be less than or equal to square root of double integration f square into double integration g square, and the left hand side and the right hand side will be equal whenever g is equal to c times f. Otherwise, left hand side will always be less than the right hand side. So, this also says that whenever f or the template is similar to a region of the given image g with a multiplicative factor of constant c, then this f into g integration will take on the maximum value. Otherwise, it will be less. If I convert this into the digital case, then the same expression can be written in the form that double summation f I j into g I j, where I and j belongs to the given region A. This should be less than or equal to square root of double summation f square I j into g square I j. Again, sorry, this has to be double summation g square I j for this I and j belonging to the region A, here also for I and j belonging to the region A. And this left hand side and the right hand side will be equal only when g I j is equal to some constant into f I j, and this has to be true for all values of I j within the given region. So, for this template matching problem, we have assumed that f is the given template and g is the given image, and we have also assumed that f is less than, or the size of f is less than the size of the given image g. Now, again from the Cauchy-Schwarz inequality, so I go back to this Cauchy-Schwarz inequality. What we get? That double integration f x y into g x plus u y plus v into dx dy should be less than or equal to double integration f square x y dx dy into double integration g square x y into dx dy. No, sorry, this should be this into double integration g square x plus u y plus v dx dy. Now, the reason we are introducing term these two variables u and v is that whenever we try to match the given pattern f against the given image G, we have to find out what is the match measure or the similarity measure at different locations of G. So, for this f has to be shifted at all possible locations in the given image G, and that shift, the amount of shift that has to be given to the pattern f to find out the similarity measure at that particular location, we introduce these two shift components u and v. So, this says that shift along x direction is u and shift along y direction is v. So, here in this expression, the similarity between the given template f and the image G with a shift u and v is computed, and this is computed over the given region A. Now, because this f x y is small and the value of f x y is 0 outside the region A, so we can replace this left hand side by an integration of this form f x y into g x plus u y plus v into dx dy. And as I said that because f x y is 0 outside the region A, so this definite integral, the integral over A, can now be replaced by an integral from minus infinity to infinity. So, this is what we get from this left hand side of the expression. Now, if you look at this particular expression, that is f x y into g x plus u y plus v dx dy, double integral from minus infinity to infinity, this is nothing but the cross correlation between f and g. And then if you look at the right hand side, this f square x y dx dy integral over A, this is a constant for a given template, whereas this particular component, that is g square into x plus u y plus v dx dy, this is not a constant, because the value of this depends upon the shift u and v. So, though from the left hand side we have got that this is equivalent to cross correlation between the function f and g, but this cross correlation directly cannot be used as a similarity measure, because the right hand side is not fixed. Though f square x y dx dy is fixed, but g square x y x plus u y plus v dx dy integral is not fixed, it depends upon the shift u and v. So, because of this, the cross correlation measure cannot be directly used as a similarity measure or a match measure. So, what we have to go for is what is called a normalized cross correlation. So, if we call this cross correlation measure f x y g x plus u y plus v dx dy integration from minus infinity to infinity, if I represent this as the cross correlation CFG, then the normalized cross correlation will be given by CFG divided by g square x plus u y plus v dx dy double integral over the region A and square root of this. So, in our previous one, so what we said is that CFG has to be the normalized cross correlation will be CFG divided by double integral g x plus u y plus v dx dy, where the integration is taken over the region A and square root of this. And you see that once I take this normalized cross correlation, this is what we are calling as normalized cross correlation. So, once we consider this normalized cross correlation, you find that CFG will take the maximum possible value, which is given by double integral f square x y dx dy, take the integral over the region A, and because this is fixed, so this region of integration is not very important. Square root of this is the maximum value which will be attained by this normalized cross correlation for a particular value of u and v, for the values of u and v, for which this function g becomes some constant c times f. So, for that particular value, that particular shift u v, where g is equal to some constant c times f, this normalized cross correlation will take the maximum value, and the maximum value of this normalized cross correlation is given by double integral f square x y dx dy and square root of this. Okay. Thank you.